Okay. Hello everyone, I'm Federico Mazzone from the University of Oldenburg, and today I'm here to speak to you about this work of ours. It's about time series and how to perform secure change point detection in a privacy-preserving way. For the people like me that have a very short attention span, here is a very quick summary of the entire work. The task we faced is change point detection, that I will tell you later what it is, but the idea is to study structural changes in time series data. The setting that we faced is secure outsourced computation, but can be extended to many other settings, including multi-party computations. The approach, as you can imagine from the title, is via fully homomorphic encryption. Specifically, we used CKKS. And our key achievement is to face the usual computational bottleneck of FHE. And our most valuable result is to be able to process time series with in the order of 1 million timestamps within 3 minutes on a relatively decent sized cluster. So here is the actual presentation. First of all, for the people who might not be familiar with this data format, what is a time series? Well, you can think about it as just one-dimensional data stream. Usually you can imagine it just like sampling some form of data over time. And this is the usual graphical representation, value over time. This can appear in many contexts. Medical settings, first of all, like EEGs or heartbeat, but you can also have these within, for instance, cybersecurity analysis, like one of the data sets we used for our evaluation was about detecting anomalies in network traffics. But yeah, what is exactly that we want to do here? We want to be able to automatically identify when a time series changes something. That something can be multiple things. In general, is when it changes behavior. And you can imagine this as assuming that up to a certain point, the time series was being drawn from a certain distribution. And after a certain point, it was drawn from a different distribution, where different can be whatever. And you want to identify this change point as accurately as possible. The setting, as I was telling you, the one that we focus, at least just for the explanation, is going to be outsourced CPD. So you can imagine a data owner who retrieves, collects some data. For whatever reason, they cannot process it locally because they don't have the resources or because they have some form of legal constraints for which they have to outsource it anyway. So ideally, you want to be able to send this time series data to a computing server. The computing server will perform the change point detection and send the result back. As you can imagine, since we are all in security here, this can be kind of privacy issues in some sense, in some contexts. So there are many possible privacy-enhancing technologies to do this, and what we decided to adopt here was, as mentioned before, homomorphic encryption. So you're going to have the data owner, as usual, generating the key pairs and all the evaluation keys, sending them to the computing server, and the computing server will be able to perform the entire change point detection protocol under the encryption layer. To go on and explain to you exactly how we did this, I have first to tell you what change point types we faced. We mainly tackled 3 different types of change point. A change in the mean of the distribution, so you assume the same distribution, but at some point the mean changes, or a change of variance, or a change of frequency. How do we actually perform the change point detection? Well, the algorithm was already there. We just let's say, made it a bit more FHE friendly to avoid to make it run for 1 month over 60,000 points. The first step is to split the time series data. There is apparently an optimal split which has been proven to be square root of n, where n is the size of the time series data. So you just split the time series in chunks. Now you want to compute for each chunk what we call a summary statistic, and this depends on the type of the change point you want to identify. For instance, if you want to identify a change in mean, then the summary statistic is going to be quite straightforward. It's going to be the mean within each block. Similarly for the variance, while to identify change point in frequency, it's a bit more convoluted. You have to count how many triplets are following a specific pattern. In particular, you want to count how many triplets are in the form up and down or down and up, because depending on how many times you can count them with respect to how many triplets there are, that tells you how often the time series goes up and down, and that is directly correlated to the frequency of the time series data itself. The technical details on how to do this under CKKS, they are not straightforward. As you can imagine, they heavily rely on being able to compare two values under FHE, which is, again, computationally quite intensive. We used some previous results on how to perform ranking computation. And yeah, for this kind of details, feel free to approach me later on. Final part, once we get this kind of summarized statistics, so we get a new time series with length square root of n, each element being the related, the corresponding summary value, then what you're going to do is substantially perform a mean change point detection. And for this, you can directly use a well-known method that is called cumulative sum statistic. Again, this involves other quite FHE unfriendly computation. You can see an absolute value, you can see an argmax. Optimizing this was the main challenge. We managed to do that by fully exploiting the SIMD capabilities of CKKS to parallelize as many computations as possible. Just to show you real quick some of our results. This is our scalability analysis. As you can see, we are able to, as you can see, first of all, the frequency shift analysis is much more computation intensive than the other two, as it requires that additional triplets comparison I told you before. It scales quite nicely. Once we get to 1 million points, frequency is around 3 minutes, while mean and variance are almost below 2 minutes, 2 minutes and a half. As for accuracy, we are perfectly identical to the plaintext baseline, meaning that the approximation of all the comparison and all the non-polynomial function was close enough to give us perfect accuracy. However, we noticed that this was not holding anymore for real-world dataset, for which we were getting a slight relative error over the plaintext baseline, and the plaintext baseline also had a slight relative error over the ground truth that was identified by human experts. Last slide. We compare this with other technologies, specifically with differential privacy, which was the only other competitor at the moment, in particular with local differential privacy because of our outsourced computation setting. As you can see, that was quite heavy in terms of accuracy loss for the differential privacy, especially for epsilon below 10, no matter of the size, even with the relatively large size time series for which normally differential privacy is quite good with. That is it. So if you want to give a look at the paper, here it is. And if you want to reach me out for questions, feel free to approach me at the poster, and I will take just 10 more seconds if I can. I will use a quick advertisement. If you are interested in working on these topics, also as potential PhD students, so if you know good master students, we are looking for one at the moment at the university, so feel free to reach me out for that as well. Thank you very much.